There is something profoundly human about our desire to see things as they truly are, to peer beyond appearances and grasp the underlying reality of the world around us. From ancient times, philosophers and scientists have asked what lies beneath the surface, what exists when no one is looking, what reality truly is independent of our observations. I have spent my entire life grappling with these questions, and I must tell you something that may surprise you. Quantum mechanics has taught us that there are fundamental limits to seeing reality, limits that are not imposed by the weakness of our eyes or the crudeness of our instruments, but by the very nature of reality itself. These limits are not temporary obstacles to be overcome by better technology. They are permanent features of how the universe is structured at its most fundamental level. Let me take you back to the beginning of my journey into this strange territory. When I was a young student in Copenhagen at the turn of the 20th century, the question of atomic structure was just beginning to come into focus. We knew atoms existed, we had evidence from chemistry and from experiments on Brownian motion, but we had no clear picture of what they looked like inside. Were they solid spheres? Were they made of smaller parts? Could we ever truly see them? J. Thomson had discovered the electron in 1897, showing that atoms contain negatively charged particles that could be removed. He proposed what people jokingly called the plum pudding model, where electrons were embedded in a positively charged sphere like raisins in a dessert. Then came Ernest Rutherford's extraordinary gold foil experiment in 1909, where he fired alpha particles at thin sheets of gold and discovered that most passed straight through while a few bounced back at sharp angles. This could only mean that atoms had a tiny, dense, positively charged nucleus with electrons somehow arranged around it. When I went to work with Rutherford in Manchester in 1912, I became fascinated by this nuclear model, but I also recognized its fundamental problem. If electrons orbited the nucleus like planets around the Sun, classical electromagnetism said they should radiate energy continuously and spiral into the nucleus in a fraction of a second. Every atom should collapse instantly. But atoms are stable. They exist for billions of years. Something was deeply wrong with our ability to see what was really happening inside the atom. My solution was to propose that electrons could only exist in certain discrete orbits, stationary states where they would not radiate despite being in accelerated motion. Electrons could jump instantaneously between these orbits, emitting or absorbing light in the process. This explained atomic spectra beautifully, but it also introduced something profoundly strange. What happened during these quantum jumps? The electron disappeared from one orbit and appeared in another without passing through the space between. There was no trajectory to see, no continuous path to visualize. The electron's motion between orbits was fundamentally invisible, not because we lacked the tools to observe it, but because there was nothing there to observe. The transition was discontinuous, instantaneous, unvisualizable. Even as I celebrated the success of my atomic model, I knew it was incomplete. I was still trying to see reality in classical terms, imagining electrons as little particles following definite paths, even if those paths were restricted to certain allowed orbits. But as quantum mechanics developed through the 1920s, it became clear that this entire way of thinking was inappropriate. Reality at the atomic level simply does not have the character we attribute to it based on our everyday experience of seeing macroscopic objects. Werner Heisenberg, working with me in Copenhagen, developed matrix mechanics in 1925. He insisted that physics should deal only with observable quantities, with things we can actually measure in experiments, not with unobservable trajectories or positions between measurements. Around the same time, Rowan Schrödinger developed wave mechanics, treating electrons not as particles following paths but as waves described by a wave function that spreads through space. These two approaches looked completely different but turned out to be mathematically equivalent. Schrödinger's wave function revolutionized how we think about seeing reality. The wave function is not something we can see directly. It is a mathematical object, a complex-valued function that encodes probabilities. The square of the wave function's amplitude at any location gives the probability of finding the electron there if we measure its position. But before we measure, the electron does not have a definite position. It is not hidden somewhere with us being ignorant of where. Rather, the electron is in a superposition of being at many locations simultaneously, and the wave function describes this superposition. This is where the limits of seeing reality become starkly apparent. What does an electron look like before we measure its position? There is no answer to this question in the usual sense. The electron is spread out, existing in a quantum superposition that has no classical analog. We cannot see this superposition directly. We can only see the consequences when we perform measurements, when the wave function collapses and the electron manifests at a specific location. The electron's state between measurements is fundamentally invisible to us, not because we are not looking carefully enough, but because it does not have the kind of definite, visualizable character that we associate with seeing things. Heisenberg's uncertainty principle, discovered in 1927, made this even more precise. The principle states that we cannot simultaneously see both the position and momentum of a particle with arbitrary precision. The more precisely we determine one, the less precisely we can know the other. This is not a statement about the disturbance our measurements cause, though Heisenberg initially described it that way. It is a statement about what can exist in definite form. Position and momentum are represented by mathematical operators that do not commute, meaning they cannot both have definite values at the same time. So what are we seeing when we look at an electron? We are not seeing the electron as it is in itself, independent of our observation. We are seeing the result of an interaction between the electron and our measuring apparatus, an interaction that brings into definite existence a property that did not exist in definite form before the measurement. This is radically different from classical physics, where we assume that objects have all their properties at all times and that measurement simply reveals these pre-existing properties without fundamentally altering them. The double-slit experiment illustrates these limits to seeing reality with beautiful clarity. When we send electrons one at a time through two slits, each electron arrives at a screen on the far side at a specific point, like a particle. But as we repeat the experiment many times, the accumulated points build up an interference pattern, alternating bands of high and low density, like waves. This can only be explained if each electron somehow passes through both slits simultaneously and interferes with itself. Now, can we see which slit each electron goes through? If we place detectors at the slits to observe the electron's path, we can indeed determine which slit it passes through. But the moment we do this, the interference pattern disappears. We get two simple bands on the screen, consistent with electrons behaving as classical particles going through one slit or the other. The very act of trying to see which path the electron takes changes what we see in the final result. This is not because our detectors are clumsy or disturbing. Even the most gentle possible observation has this effect. The fundamental issue is that seeing which slit the electron goes through and seeing the interference pattern are mutually exclusive. You can design your experiment to see one or the other, but never both simultaneously. Both pieces of information are real and important for understanding the electron, but nature prevents us from seeing both at once. This is what I called complementarity. I spent many years developing and defending this concept of complementarity because I believed it was essential for understanding the limits of seeing reality. Wave and particle properties are complementary aspects of quantum objects. We can see one aspect or the other depending on our experimental arrangement, but we can never see both simultaneously because the experimental setups required to observe them are mutually exclusive. Both are necessary for a complete description, but they cannot be unified into a single visualizable picture that we can see all at once. Albert Einstein deeply resisted this conclusion. He felt that physics should describe reality as it is, independent of observation, and that we should be able to see, at least in principle, what is really happening at all times. We had many profound discussions about these matters. Einstein would propose thought experiments designed to show that quantum mechanics led to absurdities or contradictions. I would respond that the apparent absurdities arose from trying to impose classical concepts of seeing and reality onto quantum phenomena where they did not apply. The most famous of these debates involved the EPR paradox in 1935. Einstein, Podolsky, and Rosen showed that quantum mechanics predicted correlations between distant particles that seemed to require instantaneous influences across space. They argued that if we measure one particle and instantly know something about a distant particle, then that property of the distant particle must have existed all along, even though quantum mechanics said it did not have a definite value before measurement. They concluded that quantum mechanics must be incomplete, that there must be hidden variables determining these properties that we simply cannot see. I argued that Einstein was making an unwarranted assumption about what it means to see reality. He assumed that properties exist in definite form independent of measurement, waiting to be seen. But quantum mechanics suggests that properties are brought into definite existence by the act of measurement. Before we measure the spin of an electron, it does not have a definite spin. The measurement does not reveal a pre-existing spin that we could not see before. It creates a definite spin from quantum possibilities. For decades, this remained a philosophical debate. But then John Bell developed a mathematical test that could distinguish between quantum mechanics and any theory with local hidden variables that would let us see reality, as Einstein imagined. Bell's theorem showed that any such theory must satisfy certain inequalities in the correlations between measurements on distant particles. Quantum mechanics predicts violations of these inequalities. Beginning in the 1970s and continuing to this day, experiments have consistently confirmed the quantum predictions and violated Bell's inequalities. What does this mean for our ability to see reality? It means that Einstein's vision of a definite, observer-independent reality where particles have all their properties at all times, just hidden from our view, is incompatible with experimental results. The properties we observe are not pre-existing features that we uncover through measurement. They are brought into definite existence through the measurement process itself. Reality at the quantum level does not exist in the definite, visualizable form that classical physics assumed. This has profound philosophical implications. It means that the ancient dream of seeing things as they are in themselves, independent of our observations, is not achievable at the quantum level. We can never see the electron's trajectory through the double slit when we are not measuring it, because there is no definite trajectory. We can never see both position and momentum precisely at once, because they do not both exist precisely at once. We can never see both wave and particle properties simultaneously, because they require mutually exclusive experimental arrangements. Some people find this deeply disturbing. They feel that physics should give us an objective picture of reality that exists whether we observe it or not. But I came to see it differently. The limits to seeing reality are themselves information about reality. They tell us that reality at the quantum level has a structure that is fundamentally different from the classical world of our everyday experience. Recognizing these limits is itself a form of seeing, a way of understanding how nature actually is rather than how we wish it to be. Let me give you another example that shows these limits vividly. Consider a quantum system in a superposition of two states, say an electron with spin pointing up and spin pointing down along some axis, combined with equal amplitudes. Before we measure, we cannot see which state the electron is in because it is genuinely in both states simultaneously. This is not ignorance on our part. The electron truly does not have a definite spin until we measure it. When we perform a measurement, we see a definite outcome, spin up or spin down. But here is the strange thing: we cannot predict which outcome we will see in any individual measurement. Quantum mechanics only gives us probabilities. The outcome is fundamentally random, not determined by any prior state or hidden variable that we failed to see. We can repeat the experiment many times with identically prepared systems and get different results each time, with the outcomes distributed according to quantum probabilities. This means there is something about physical reality that is fundamentally hidden from us, not because we are not looking carefully enough, but because it does not exist in definite form until the measurement occurs. We cannot see which outcome will occur before the measurement because this fact does not exist until the measurement creates it. The future is not merely unknown but undetermined at the quantum level. This indeterminacy troubled many physicists. They felt that surely there must be some deeper level of reality that determines these outcomes, some hidden variables that we cannot see that make everything deterministic if only we knew them. But Bell's theorem and subsequent experiments have ruled this out. Nature genuinely has fundamental randomness built into it at the quantum level. We cannot see what determines the outcome of a quantum measurement because nothing determines it beyond the probabilities encoded in the wave function. The process of measurement itself represents another profound limit to seeing reality. In quantum mechanics, measurement plays a special role. The wave function evolves smoothly and deterministically according to Schrödinger's equation when no measurement occurs. But when we perform a measurement, the wave function collapses discontinuously and randomly to one of the possible outcomes. This collapse is not described by Schrödinger's equation. It is a separate postulate, a different kind of process. What exactly counts as a measurement? Where is the boundary between the quantum system evolving according to Schrödinger's equation and the classical measuring apparatus that records definite outcomes? This is the measurement problem, and it represents a fundamental limit to our ability to see what is really happening in quantum mechanics. We use quantum mechanics to make predictions with extraordinary precision, but we cannot fully see or understand the measurement process itself within the quantum framework. Some interpret this as a failure of quantum mechanics, suggesting we need a deeper theory. But I always emphasize that we must maintain a distinction between quantum and classical descriptions. We need classical concepts to describe experimental arrangements and communicate results. We say the pointer points to this number on the dial. We say the particle hit the screen at this location. These are classical statements using ordinary language. But the quantum system before measurement is not described classically. It is described by wave functions and superpositions. The measurement process bridges these two domains, the quantum and the classical, and this bridge may be irreducible. We may never be able to see measurement purely in quantum terms because seeing itself requires classical concepts to describe what we observe. This is not a temporary gap in our knowledge but a recognition that knowledge has levels and that seeing always involves both the quantum system and the classical context in which we observe it. There is also a practical limit to seeing reality that comes from complexity. Even if we knew the complete wave function of a macroscopic object, calculating its evolution would be impossible. The wave function of a system with many particles exists in a high-dimensional space, and tracking it requires resources that exceed anything available in the universe. We must use approximations, statistical methods, effective theories that ignore most details. This means that even in principle, with perfect quantum mechanical knowledge, we cannot see the detailed behavior of complex systems. We can see certain features, certain patterns, certain statistical regularities, but not the complete microscopic reality. This is not just a practical limitation of computers or mathematics. It is a fundamental feature of how information and computation work in our universe. Moreover, quantum mechanics tells us that certain kinds of seeing are fundamentally impossible through theorems like the no-cloning theorem, which says we cannot make a perfect copy of an unknown quantum state. If we could extract more information than the uncertainty principle allows. This means that seeing quantum reality in certain ways is prohibited by the logical consistency of quantum mechanics itself. I want to be clear that these limits to seeing reality are not deficiencies or failures. They are positive insights into how nature works. When I say we cannot see the electron's path through a double slit when we are not measuring it, I am not confessing ignorance. I am stating a fact about reality. There is no definite path to see. When I say position and momentum cannot both be seen precisely, I am not describing a limitation of our instruments. I am describing how quantum states are structured. These limits tell us that reality at the quantum level is not made of things with definite properties that exist whether we observe them or not. It is made of quantum states, superpositions, probabilities, complementary aspects that require different experimental contexts to manifest. We can see these aspects, we can measure them, we can verify them experimentally, but we cannot see them all at once in a single unified classical picture because that is not how quantum reality is structured. Some physicists have tried to restore the ability to see reality in classical terms through alternative interpretations of quantum mechanics. David Bohm developed a theory with hidden variables where particles have definite positions and follow definite trajectories guided by a quantum potential. Hugh Everett proposed many worlds where every measurement causes the universe to split into branches corresponding to different outcomes. These interpretations are mathematically consistent, but they seem to me to add unnecessary complexity to avoid accepting what quantum mechanics is straightforwardly telling us about the limits of seeing reality. Throughout my career, I tried to help physicists accept these limits not as defeats but as discoveries. We have discovered that seeing reality has fundamental constraints imposed by nature herself. We have discovered that complementarity is real, that position and momentum cannot both be definite, that wave and particle aspects cannot both be observed simultaneously, that measurement plays an irreducible role in bringing properties into definite existence. This does not mean we cannot understand nature or that physics is impossible. Quite the contrary. Quantum mechanics is the most precisely confirmed theory in the history of science. We can predict atomic spectra, chemical reactions, the behavior of materials, and countless other phenomena with extraordinary accuracy. We can build technologies based on quantum mechanics that have transformed our world. All of this is possible not despite the limits to seeing reality, but because we have learned to work within these limits, to ask the right questions, to design experiments that reveal what can be revealed while respecting what cannot. The limits of seeing reality are not obstacles to knowledge but features of knowledge at the quantum level. We know that certain questions have no answers because they presuppose concepts that do not apply. We know that certain combinations of properties cannot be observed simultaneously. We know that measurement affects what we measure in fundamental ways. All of this is knowledge, hard-won through careful experiment and rigorous theory. I think back to my early days working on the atom, when I first encountered the puzzle of quantum jumps and wondered what was really happening as electrons moved between orbits. I wanted to see the process, to visualize it, to understand it in classical terms. But quantum mechanics taught me that this desire was based on inappropriate expectations. There is nothing to see in the jump because the jump is not a continuous process in space and time. It is an instantaneous transition between quantum states. Learning to accept this, learning to think in quantum terms rather than demanding classical pictures, was difficult but essential. And it opened up a new way of relating to nature, one that respects her fundamental character rather than trying to force her into our preconceptions. The limits of seeing reality are not barriers that prevent us from knowing nature. They are features of nature that we come to know by bumping up against them, by learning what can and cannot be observed, by discovering how quantum mechanics constrains what is possible. Reality at the quantum level refuses to be seen in the way we see macroscopic objects, and this refusal is itself revealing. It tells us that the quantum world is genuinely different, operating according to principles that have no classical counterpart. Our eyes and instruments evolved to see the classical world where quantum effects average out and become invisible. We should not expect these tools, even refined and enhanced, to let us see quantum reality in the same direct way. Instead, we see quantum reality indirectly through measurements that bring definite classical outcomes from quantum possibilities, through mathematical descriptions that predict probabilities, through complementary aspects that reveal themselves in different experimental contexts. This seeing is not less real or less valid than classical seeing. It is simply different, appropriate to the quantum character of what we are trying to see. The limits of seeing reality are fundamental because reality itself, at the quantum level, has a fundamentally different structure than classical reality. It is not made of objects with definite properties that persist through time whether observed or not. It is made of quantum states that exist in superpositions, that have complementary aspects, that only manifest definite properties through interaction and measurement. Seeing this reality means accepting these features, working within these constraints, and recognizing that the limits themselves are information about how nature is actually constituted. This is what quantum mechanics has taught us about the limits of seeing reality, and it is one of the most profound lessons in the history of science. We cannot see reality as it is in itself, independent of observation, because at the quantum level there is no such independent reality with all properties defined. What we see depends on how we look, on what we choose to measure, on the experimental context we create. And this context dependence is not a bug but a feature, not a failure of seeing but an insight into the nature of quantum reality itself.